This lecture is going to be about the kinetic molecular theory of gases, which is basically a molecular idea of how gases behave. The kinetic molecular theory of gases. Understand kinetic molecular theory as it is applied to gases, especially the distribution of molecular speeds, which is, well, proportional to the energy. So the book gives you three parts for the molecular theory of gases, kinetic molecular theory. I give you four parts, and I want you to remember these four parts. So first of all, the space between gas particles is much greater than the size of the particles. If you look at the boxes I've drawn that show gas particles in a box, there's a lot of space between the gas particles. So what's in that space, you might think? Is air in that space? And the answer is no, nothing is in that space. So you could consider it to be a vacuum. So gases are mostly empty space. So what happens if you take those particles and squeeze them together more closely? It's an easy thing to do because there's space between the molecules. So therefore, gases are easily compressed. Secondly, gas particles are in constant, random, and rapid motion. A gas particle will move in a straight line until it hits something else and then bounces off and it moves in a straight line again. So what does this mean for gases? Well, it means that gases easily mix, or you could say that if you open a can of something that's very fragrant, the gas particles diffuse very quickly and they go in all directions. Now, that doesn't mean that the odor is going to be as strong, because when you take that gas and it diffuses, the concentration of the gas particles goes down, which means it won't smell as strong. Collisions of gas particles do not lose kinetic energy. So this means that when the particles hit one another, or when they hit the side of a container, they don't lose energy. That's what they're saying. And gases behave pretty much that way. The fact of the matter is, if you don't change the pressure or the temperature on a container of gas, the gas is going to stay a gas. However, do they lose energy? And the answer is, well, yeah, they do, but they behave like they don't. For instance, if you take a Super Bowl that you get from like one of those little machines in the supermarket where you put in a dime or a quarter and you get this little bouncy ball that'll bounce really high. Well, those bouncy balls are kind of like gas molecules. If you drop a ball from, whatever height and let go of it without throwing it down, just let go of it, it bounces up pretty high, but not all the way back to where you had left it. Now, why doesn't it jump all the way back up? And the answer is it loses energy in the form of friction with the ground. That friction heats up the ground, so energy is lost due to heat. So that happens every time a molecule hits something. You lose energy due to heat. So the molecules of gas appear to not lose any energy due to heat. And that way gases stay gases. So if you have a container with a gas in it and you don't change the pressure and you don't change the temp, it will stay a gas. Imagine if they did lose energy. If they did lose energy like that Super Bowl, that means that all gas molecules on Earth by now should have lost energy and become liquids. And presumably the liquids would have lost energy and become solids. Can you imagine what life would be like if there was no atmosphere, but instead there was just a liquid oozing over the whole layer of the world? We would have gills. It'd be a whole different world. The average kinetic energy of a gas is proportional to the Kelvin temp. Now, what this means is that any gas, if you have the same amount, will have the same kinetic energy. So molecules that are small will have the same amount of energy that are molecules that are large, if you have the same amount and at the same temp. So how can that be? And the answer is simple. The small molecules are moving fast and the big molecules are moving slow. Let's take a look at that temperature idea for two molecules of O2 at different temps. So we're looking at the kinetic energy and the temperature relationship. So we're looking at molecular speed and kinetic energy. So here we have this formula that says kinetic energy, Ke, is equal to the mass times the speed or velocity squared over 2. So m is the mass in grams and u is the speed in meters per second. So we would say that the kinetic energy is proportional to the mass, and the kinetic energy is proportional to the square of the molecular speed. Okay, so what this means is if you increase the temp, you're going to increase the speed, and if you increase the speed, you increase the kinetic energy. So here's the chart that kind of shows you that. If you look at O2 at 25 degrees Celsius, and we look at the molecules here, we have on the y-axis the number of molecules, and on the x-axis the speed. So here, when we have O2 at 25 degrees Celsius, you can see that there are a whole lot of molecules with a very small speed. But when you heat up the molecules to 1,000 degrees Celsius, there are very few molecules with this low speed, a lot more at this middle speed, if you will, and a few at this even higher speed. Okay, so this is what happens when you heat up molecules. When we take a look at this formula here, when you heat up molecules, do you change their mass? No. So what happens is you increase their speed. Let's look at the effect of molecular mass on the distribution of speed. So these are all molecules presumably at the same temp, and presumably they all have the same kinetic energy. Okay, so when we take a look, the idea is that underneath this graph, there's the same number of molecules of O2 versus N2 versus H2O versus helium. So if they all have the same kinetic energy, but they have different masses, how is it that they have the same kinetic energy? And the answer is really simple. If you take a look, the molecular speed of large molecules is on average smaller than the molecular speed of small molecules. So here, this is how they can have the same kinetic energy at the same temp. The small molecules are moving very fast or quickly, high velocity, and the large molecules are moving more slowly. Now, this is for a mole of gas particles. So the kinetic energy of 1 mole of gas particles is equal to a mole times this mu squared over 2. Now here things are a little bit different. Here we have a bar over the Ke. The bar over the Ke means that we're looking at the average kinetic energy, because if we take a look at this previous plot here, you'll notice that the different, when we look at a molecule here, let's just focus on O2 here, they don't all have the same velocity. There's a distribution of velocities. So we're looking at the average of all of these together, or the mean, as we would say. Okay, so this u squared with a bar over it is you take each velocity, you square it, and then you average the squares. That's what this is. So this is called the mean square, where u is the mean and 2 is the square. Well, actually, I should say the bar is the mean and the 2 is the square. So this is the mean square velocity. And you can think of it as being like the average of the square of the velocity. Now, since the molar mass of a molecule equals 1 mole, and since 1 mole is Avogadro's number, essentially we can take this equation and say, okay, we're going to substitute the molar mass for this n sub a times m. So we have the molar mass, kinetic energy is the molar mass times the square of the velocity, the mean square over 2. Now also there's another formula that the book gives you that the average kinetic energy is 3RT over 2, where for this particular formula, we use yet another form of R, and it's this, 8.314 joules per K per mole. Now, if kinetic energy is equal to both of these, we can set this equal to this, as I've done here below. And here, when we simplify this, we get that the mean of the velocity squared is equal to 3RT over the molar mass. And then if we take the square root of the velocity, the mean of the velocity squared, we get the square root of 3RT over the molar mass. The idea here is that if you take the velocity and square it, and then average all of those, and then take the square root, you essentially have the average velocity. So this is actually termed the root mean square speed. So root mean square speed, or the RMS speed. Now, if you wanted to ask me why we do this instead of just saying, hey, why don't we just average the velocities? There is a physical reason for doing it. And if you want to understand that physical reason, you want to take physics, which I don't teach. Okay. So let's take a look at using this formula where we're actually asked to calculate the RMS speed of oxygen molecules at 298K. So let me get a clean piece of paper here. We're going to use this formula here where we have the root mean square speed is equal to 3RT over the molar mass. So that's the formula we're going to use for this one. Calculate the RMS speed. That's this RMS speed. So that's this whole thing on the left of oxygen molecules at 298K. So we're going to use 3 times 8.314 joules per K mole. And the temperature is going to be 298K. And on the bottom, we have the molar mass of oxygen, which is 32.00 grams per mole. Okay, so let's see if everything cancels out. That should cancel out. So mole cancels out, K cancels out, and joules, remember a joule is equal to a kilogram meter squared per second squared. So here, looks like we need to change this into kilograms or change this into grams. And here, what I'm going to do is I'm going to take 32.00 grams multiplied by 1 kilogram per 1,000 grams, and we get 0.032 kilograms. So I'm going to cross this out, and I'm going to write down 0.032 kilograms so that this kilogram can cancel that kilogram, and we'll put our numbers in now. Clear? 3 times 8.314 times 298 divided by 0.032. So the way I'm going to think about this is 3 times 8 is around 24, but because of that 0.3, I'll make it 25. So I have 25 times 298, which is 25 times 300. Now, how do I do 25 times 300? Well, I can't, but I can do 25 times 3 is 75, and then add the 2 zeros. So that's 7,500. Now, 7,500 divided by 0.035, I know is going to be a huge number because 0.032 will go into 1 10 times, okay? Or actually, it'll go into 1 30 times. So basically, I have to take my 7,500, multiply it times 30, and let's see. So I'm going to have to do 75 times 3 is 225, and then add 3 zeros. So we're talking about 225,000 for an answer. And then we have to take the square root of that. So what's the square root of 225,000? I don't know. So let's see. Let's make it the square root of 24. And then we have to multiply times 100. So what's this? What time 1 is 24? We'll call it 5. So the answer is around 500 meters per second, if I've done this right. So let's go ahead and do this stuff on the inside first. 3 times 3 times 8.314 times 298, and then divided by 0.032. So here we get the square root of 0.72, and that's going to be meters squared per second squared, okay, because the kilograms are going to cancel here, and we're left with meters squared per second squared. Okay, so I said this would be around 250,000. Clearly, I was a little bit off, but now we're going to take the square root of that. So let's see, how do I do this on this calculator? I think what I'll do is I'll do caret 1/2. That's the square root. Okay, so we get 482. And what happens to the meter? It becomes meter. The meter squared becomes meter when we take the square root. And the square root of per second squared is second. So we get, oops, I put second squared there. So this is going to be our root mean square value. So what is the take home here? The take home. 1, get the mass, or get the molar mass in kilograms per mole. Okay, we want kilograms per mole rather than grams per mole. That's the real take home. And then of course you need to remember that R is equal to 8.314 joules per mole per K. And the temperature has to be Kelvin. And then you're good to go. All right. Thank you for listening.